In this part of physics, we are going to talk about energy band theory, and based on it, how we classify materials into conductors, semiconductors, and insulators. And we're going to talk about semiconductors and types of semiconductors, intrinsic and also extrinsic. As a result of semiconductors, we're going to see how they lead into diodes and what is p-type and what is n-type of diodes, and also we're going to talk about transistors. Okay, for energy band theory, as we know, in general, materials are classified into conductors, semiconductors, and insulators. And we know that conductors that can conduct electricity and heat easily, while semiconductors into a specific degree, they can conduct electricity and not that easy way for them to conduct electricity as it is for conductors. And for insulators, as we know, it is very difficult for insulators to conduct electricity. Okay. Conduction of electricity, it depends on the free electrons or the valence electrons of the materials or of the elements. If you go into the periodic table, as here now, as you see, this is the periodic table, and then these ones are all the available elements. We see that on the periodic table, elements are ordered based on their atomic number. So hydrogen here, the first one, because it has atomic number 1, and that means it has 1 electron and 1 proton. And we know that the atoms in general, they have a nucleus here, and around it there are shells. So if we are talking about here, for example, the lithium, as you see here, lithium here, it has 3. That means it has 3 atomic number. That means it has 3 electrons, 3 protons. We're going to talk about electrons, how these electrons are located or how they are placed in the atom. 2 electrons are in the first shell and 1 electron in the third shell. So this electron that is in the third shell, its attraction to the nucleus is weak. So that means this electron now has higher ability to move. So in this case now, lithium can be a conductor, because now when it has electrons that are able to move, that means they can move with just a specific or small amount of voltage applied. These electrons will move. And movement of electrons, it means what? It means electricity. So they are conductors. If we are talking on the other side about, for example, oxygen here, it has 8 atomic numbers. So that means on the first shell, as we know, 2 here, and in the second shell there are here 1, 2, 3, 4, 5, 6 electrons. So these 8 electrons are located exactly in this way. So as you see now, these electrons that are on the second or on the valence electron here, they are 7 or 6 electrons. And here that means the charge of the nucleus, that means it has 8 protons, so that means it's positive 8. It's positive 8, the charge of the nucleus. And here is the charge of the nucleus is what? Is positive 3 for lithium. So in this case now, since both of them, they have 2 shells. This one, as you see, it has 2 shells, and here this one has what? 2 shells. So if the atom has the same number of shells, so in this case, the greater the charge of the nucleus, the greater the force of attraction for the valence electrons. So in this case now, for the oxygen, the attraction between the electrons on the outer shell here, these ones that are 6 electrons, and the nucleus is very high compared to the lithium. So that means these electrons now of the oxygen, it's not easy for them to move or to leave their atoms. So that means in this case, when they cannot move, that means they cannot make flow of electrons. In this case, it's hard for them what? To conduct electricity. Okay, this is now if we are talking about just one atom, and one atom is reflected also to when they are many atoms. Like now, if we have a piece of lithium or a group of another element that is non-metal. As we know, these ones metals here in general, they are conductors, but non-metals here in general, they are not conductors. And here we have some elements that they are semiconductors. That means to a degree, they can conduct what? Electricity. So if we are talking about now a group of atoms, that means an element with a group of elements. How can we classify now elements based on conductivity? So we have energy band theory. Energy band theory, it's just like a figure that represents how materials are conductive or not. Just instead now of going into each element here and to understand what is its inner structure of electrons and to see they are able to conduct electricity or not. So it's hard to go for each element to see how conductive is it based on its what? Inner valence electrons. So we have just now, which is energy band theory. It gives us just the figure, and based on the figure now, we can understand that this element is a conductor or semiconductor or insulator. How does that happen? So in general, if we see this shape now, I tried to make it as easier as possible for you to understand it. So here, for example, now I have here an element. Here I have what? An element. I'm going to make it red. Here now I have an element. And the element now has many, as we know, billions of atoms. So this element now here, a piece of element, the electrons around that means the electrons of this metal now will be in this band. This one, for example, we call it what? A band. This is band. Okay, this band now, these electrons, this one we call it valence band. We call it what? Valence band. So these electrons in general of this metal, they are around the nuclei. So that means in a band or in a layer that we call this layer what? Valence band. Okay, this is now the first band around the metal or around the material, whatever is it, a metal or non-metal or a metalloid. So this one now is called what? Valence band. Okay, what is the second layer? What is the second layer around that element? Which is this one here, and we're gonna call it what? We're gonna call this one what? Gap energy. We're gonna call it gap energy band. Gap energy what? Band. Okay, what is the third band, which is this one here? This energy, with this one here, we call it conduction what? Band. Okay, now, if electrons, and this is now the ideas of energy band theory, if electrons around the material are available inside the valence band, and it's hard for them to move from the valence band into the conduction band, so this material classified as insulator. So what are insulators now? When the electrons around the material are located in the valence band and it's difficult for them to go up to higher level, that means to the conduction band, in this case we call this material what? Insulator. Okay, now what about if it is easy for them to move? If it is easy for them to move here, again, it's just here. If these electrons now, it's easy for them to go into conduction bands. In this case, this material is classified as what? As conductor. So when the electrons are easy for them to move from the valence band into the conduction band, that means they are conductors because electrons are available on the conduction band, which is related to what? The conduction. So in this case, when electrons become here, so that means they are available to move or to flow as electricity. So these ones as conductors. So we agree that insulators, it's hard for electrons to move from the valence band into the conduction band, while for conductors, it's easy for electrons to go easily from the valence band into what? The conduction band. Okay, now what is the energy gap? Energy gap, it represents the energy between these two, between the conduction band and between what? The valence band. So this band now is flexible. That means it can be small, very short. It can be big. Based on what we make it larger or smaller, it depends on the material. If the material is conductor, that means the energy, the gap energy in this case, it's going to be close to zero. That means it will not exist. That means the conduction band will be exactly above the valence band. So that means electrons are moving between conduction band and valence band easily, since there is no gap energy big between them. Okay, what about insulators? Insulators, they have a gap energy band that is big. That means if it is like a wall, like a layer that prevents electrons from going from valence band into a conduction band. And the greater the gap energy, the harder for material to be a conductor. So energy gap in generals, how long is it in electron volt if we measure it by energy unit? How big is it? It means how hard the material to be a conductor. Okay, for conductors, this gap is around zero. So that means no gap energy between conduction band and valence band for conductors. While for semiconductors, it ranges from 1 to 2 electron volt. While for insulators, it's 5 and above. So if we see another picture here that summarizes this circles into this part. Now, also it is what we are talking about around the materials. So that means here, as we said, the first band is valence band here, valence band. So on conductors, as you see here, on conductors, the conduction band and the valence band are so close to each other, like they have no gap between them. So in this case, it's easy for electrons to move from the valence band into the conductions, and they're going to be free electrons, so they can move as a flow of electrons, which is electricity. For semiconductors, you see this gap now between the conduction band is about 1 to 2 electron volt, which is the band gap. While for insulators, as you see, it's too big. That means now it's hard now for insulators. It is hard for electrons to go from the valence band into the conduction band. So this is now energy band theory. It just summarizes what happens for materials to be conductors or not. So it summarizes just for these materials for this shape only. And basically, for conductors, for metals, they are conductors. Why? Valence band and conduction band, they have no gap between them. Semiconductors, they have a gap between them that is around 1 to 2 electron volt, while for insulators, it's going to be around 5 and greater. So that means it's hard for insulators to be conductors because electrons, they have to go through big difference energy to go from one band to the next band that is related to conduction. Okay, now if we go to semiconductors now, and it is the main idea of the lesson of today. So conductors, we know them and we understand them. Insulators, okay, we know them, that it's hard for them to be conductors. And we said conductors, we know that they can conduct electricity easily. Okay, so we're going to focus on semiconductors. Semiconductors, like I give 2 examples, like silicon and germanium. These ones, 2 elements that are what? Classified as semiconductors. The energy gap now of silicon, will it be the same like for germanium? It means which one of them will be easier for it to conduct electricity. So the shorter the band gap, or we call it the energy gap band, okay, the shorter it is for the element, that means the higher conductive it is. Okay, for silicon, it's gonna be around what? Around 1.2 electron volt. While for germanium, it's gonna be 0.7 electron volt. This one now is the band gap or the energy gap. So that means now, which one is more conductive, silicon or germanium? Germanium is more conductive. Why? Because the energy gap between the conduction band and the valence band is smaller. So that means it's easier for electrons to overcome this gap than to go into what? Into conduction. Okay, in general now, semiconductors now, we can treat with these semiconductors and make them good conductors. We can make them what? Good conductors. So as we see, energy gap for germanium is 0.7 electron volt. That means now if we have here this piece of germanium now, if we heat this piece of germanium, what will happen? That means we are giving the electrons energy. When you give them energy, they will overcome the gap energy. When they overgap the gap energy, that means they'll be what? They'll be conductors. This is now how can we treat semiconductors in order to be conductors by something we call it what? Intrinsic. So that means these semiconductors, if just by heat, we can increase their conductivity. In this case, we call these ones what? Intrinsic. Intrinsic. So these ones is what? Intrinsic semiconductors. Okay, but there is another way to deal or to treat semiconductors to make them good conductors by adding impurities. That means by adding other atoms into these semiconductors. In this case, we call semiconductors that are made by adding impurities to them, we call them extrinsic. So you have two types of semiconductors. Intrinsic, which is just by heating them, they're gonna be, or we increase their conductivity, or other type, we add impurities to them, and in this case, they're gonna increase their conductivity, and we call them extrinsic semiconductors. Okay, how does that happen? Just we're gonna explain it as short as possible here. This is now the periodic table. And on the periodic table, as we see, this is, for example, as you see, this is the silicon, and here what? The germanium. This is silicon, and this is what? Germanium. And silicon, as you see, atomic number is 14. Silicon atomic number is what? Is 14. What does that mean? That means now the nucleus of the germanium, the first shell there are 2 electrons, and the second shell there are 1, 2, 3, 4, 5, 6, 7, 8 electrons, and on the third shell there are what? 2 or 4 electrons. So that means now there are 4 electrons on the third shell of silicon. Now this silicon now, in order to be stable, it has to reach the octant level of energy. Octant, that means now it has to complete this third shell to be 8 electrons. So it has here 2 traces, either to lose these 4 electrons and to be full with just 2 shells, or to add 4 electrons, and it's hard for them to add 4 electrons. So in this case, they share electrons with other atoms. So here, if we say this one now, here is silicon atom, and here another one, which is what? Another atom, and here another atom, and here another atom. As you see, these ones now are atoms of what? Of silicon. As we know, each one has what? How many valence electrons? 1, 2, 3, 4 for each atom here, as you see. So now, this middle one now, this middle one, it will make a covalent bond by these two electrons, its electron and another atom electron, and it will make one bond here, and one covalent bond here, and one covalent bond here. In this case, this middle silicon atom, it will feel like if it has 8 electrons surrounded by covalent bond by the surrounding atoms. So in this case now, the same thing this one will do here, and will do here, and will do here. So that means it will feel like if it has what? 8 electrons by covalent bond with the surrounding atoms. Okay, now what will happen? What will happen? So this is now silicon. If you go to see how atoms are inside it, you're going to see it like this, like a network of atoms adjacent to each other, and each one has a bond with the adjacent atom by what? By using 2 electrons, 2 electrons, 2 electrons. Okay, this is now silicon, and we said it is a semiconductor. How can we increase the ability of silicon to be good conductor? What will we do? Just we're gonna take one of the atoms. So this atom here, for example, which is silicon, we're gonna take it out, and we're gonna replace it by, look, by phosphorus here. And phosphorus, as we know, it has 15 electrons. That means it has 2 electrons in the first shell, and it has here 8 electrons, and it has 5 electrons in the outer shell. Okay, now if we put now phosphorus here, if we put here, instead of the silicon, we put what? We put phosphorus. We put here what? Phosphorus. As we know, phosphorus, it has 4 valence electrons. So these valence electrons, this one will be 1, and here will be 1, and here will be 1, and here will be 1, and there is 1 extra electron here, 1 extra electron here. So in this case now, in the network of the silicon, if we put several or a specific amount of impurities of phosphorus, we will get that in the whole network, we'll have many electrons that are free. When there are free electrons, too many free electrons in this network, that means now this network now becomes full of free electrons, that these electrons are ready to move. That means they are ready to make flow of electrons. So in this case, it's gonna be good conductor. Okay, how do we or how did we treat the silicon to be good conductor? By adding impurities of other or higher valence electrons like phosphorus. In this case, we had more electrons in it, so it becomes what? Good conductor. And here, the carriers of electricity will be electrons. Will be electrons. So this one now we call it N-type semiconductor. We call it what? N-type semiconductor. Why we call it N-type? Because now negatives, which are the electrons, are the carriers of charges in this semiconductor. Okay, on the other side now, what will we do? Just instead of adding phosphorus as impurities, what about if we add this silicon? You see, this is silicon. What about if we add aluminum? Aluminum here in this case, as we know, aluminum, it has 13 atomic number. So that means on the first level, there are 2 electrons. And on the second level, it had what? 8. And on the third, it has what? It has 3. So that means on the valence level, it has 3 electrons. So if we put now aluminum here, what we'll have? We'll have 3 electrons. One will be here, electron, and here electron will be here, and electron will be here. What about the third bond? It will have gap. It will be empty. So no electron there. So in this case now, when we add aluminum to silicon alloy, or that means what will happen here in this case? We'll have gaps. That means we have less number of electrons than needed for this one here. So in this case, this one now will be called positive type, and here it's gonna be conductor. But what conduct electricity here? The holes. These holes now will be holes. Imagine you have too many holes on this alloy. That means in this case, it can conduct electricity by the movement of what? Of holes. So this one we call it P type. So either we have P type or N type. It happens in what we call them extrinsic semiconductors, and it happens due to the addition of impurities, either with higher number of valence, which is going to make N type, or by the lower valence, like aluminum we added here, it's going to be then P type. Okay, now we understand now that semiconductors can be N type or P type. That means N type has many electrons as free electrons ready to move, while P type has many holes that can conduct electricity as holes. Okay, now if we have just two semiconductors close to each other, this is now a semiconductor and another semiconductor here. This one is P type and this one is N type. This one we call it diode. And diode, this is its symbol. That means it conducts the electricity in just one direction. How? We're going to understand now. Look here now what will happen. As we know, on the P type, there are too many electrons here, right? We understand N type, it happens by adding phosphorus, for example, to silicon. That means more electrons will be on that alloy. While on the positive type, we're going to have what? Holes here. Many holes, like aluminum there, when there is what? Places, there is no electrons to the N. So that means like there is less electrons than needed. So this one we call it what? P type. If we conduct now this one here into a source of what? Of electricity. Look here now what will happen. We're going to make it this way here, as you see. And here it means, this one it means positive, and this one it means what? Negative. And as we know, this is now a source of voltage. And this source of voltage is the source of current mainly. That means it supports it more to the current. How the current will move here? Keep it in mind. The negative pole, that means the electrons will move, this is their direction, will move from the negative pole into the side of the negative. They are talking about electrons. But if we are talking about the conventional current, its direction is just from the positive side. That means they move this way. They move this way, which is the gaps or the positive charges. They go out this way. Okay, if we deal now about this idea, what will happen when electrons move through this direction? As we said, when electrons move through this direction, when they come here, what will happen between these electrons and the electrons that are coming from the wire? What will happen, as we know, is what? Is repulsion, right? They repel each other. When they repel each other, that means these electrons will go here, right? These electrons will go what? There, here. And these holes will become what? Here. So electrons then here, in this place, they'll go from the N type into what? To the P type. So that means they'll go from the N type to the P type because electrons are there exactly on the same direction. So in this case, we call this connection, we call it what? Forward, by the way. We call it what? Forward connection. And this forward connection, it connects current. It connects what? Electricity. Okay, what will happen if we have another connection for this diode? If this one, as we see, this one is the diode, this one is the diode, and it has here P type, and here is N type, and N type it has, as we know, electrons, and this one it has what? Holes. Okay, if we connect them now, but look here now to the type of connection we're gonna do here. We're gonna replace them. We're gonna replace them by this way. This one is big, and this one is what? That means this one is the negative and this one is the positive pole. What will happen in this case? If we go to see the electrons now, if we are talking about the electrons, when the electrons move from this direction, right? Not the conventional current, just we are talking about the electrons. When they move here now, electrons, when they come to this point, electrons when they come to this point. What will happen at this place exactly? At this place exactly, what will happen? Where the holes will they go? To the right or to the left? So in the first one, we said electrons will move to the right, while holes then they'll move what? To the left. So in this case, they'll conduct electricity. But here now, if we are talking about this one here, as you see now, when electrons reach this point, when electrons reach this point, what will happen? What will happen in this case? So that means, as we know, electrons and holes, what will happen between them is attraction. So the holes now, in this case, here this one, it means this direction. These ones here, the holes will move to the left to meet the electrons. To meet what? The electrons. So that means the holes will move to the left to meet the electrons. So that means when the holes move to the left, they're going to get the electrons that they are coming. And here, we're going to get space. Here we'll get what? Space. And this space now, it's going to be the space between the N-type and the P-type. And since there is space there, that means no electricity is moving from the N-type to the P-type. So that means this type of connection, we call it reverse, and it doesn't what? It doesn't allow electricity to move. Again, on the right side, what we said, this connection, we call it forward. As you see, the positive is connected to the P-type, and the negative is connected to the negative side. To the negative side, yes. And in this case, you said electrons are coming here. Electrons here, they move what? Away. They move away here. They move to the right because they here repulsion. Here, repulsion. So that means they'll move to the left. And these electrons, when they move, we said, what will happen now? More electrons, they'll be here. So with these holes, these electrons will move from the left to the right. So that means there is a flow of electrons inside the diode. That means it conducts electricity. It conducts electricity. While on the other side, the poles here, the holes, as you see, will move to the left, and the electrons in general, they move also to the left. So electrons will move to the left, and here holes will move to the left. So that means between them, there will be a gap here, and in this case, no electricity will move. So first one here, what will happen? Both of them will move to the middle. So that means it's easy for them to conduct electricity. While these ones on the left, both of them will move to different directions. So they make a space between them. And it's hard then for electrons to move through the diode. So that means the diode now, it allows the current to move just in one direction when the conduction is forward, and it doesn't allow the current to move from in a different path when the conduction is what? Is reverse. So this is now, as we said, diode is made of two semiconductors. One is P-type, one is N-type. And when its conduction is forward, that means the positive to the positive and the negative to the negative, it allows current to move. While when it is conducted negative to positive and positive to negative, in this case, this is reverse conduction, and it will not allow current to move. Okay, we go now to what is called what? Transistor. Okay, what is transistor? Transistor now, it's made of three what? Three semiconductors. It can be N, P, N, or it can be what? It can be three, but here it can be what? The opposite. It can be P, N, P. What does that mean? This one means N-type and P-type in the middle and N-type. And here P-type, N-type, and what? And P-type. Transistor is used. It is a small device that is used in electronics. Mainly, it uses for many functions. One of them is to amplify the current. That means to make the current greater. These ones just will not go deep in transistors. Just what we need to know that they are made of three layers, two different layers and three layers. So different like positive and negative, but two negative and one positive, or the opposite. And it's drawn this way as a circle. And here is we have this way, as you see. And here we have what? This way. now it has 3 layers. The middle one, it is called base, and here it is called collector, and here it is called what? Emitter. So that means, as you see, it is 3 layers now. Base. That means here, this one is the base. You see, this one is the base. And one of them will be emitter, one of them will be what? Collector. Now, it can be drawn this way, and we draw here, as you see, we draw an arrow here. You see, we draw an arrow here. Or it can be in another way, drawn this way. This is collector, and this is the base, and this is emitter, and we draw the arrow this way, this direction. In this case now, how do I know if this one is NPN or PNP? How do I know? We know it through the arrow. This arrow always, it is pointing towards the negative. It is pointing towards what? The negative. So that means when it's pointing like this here, that means its pointing is towards what? Towards the base. That means the base now is the negative. When the base is the negative, that means the middle is the negative. So the other ones are what? Positive, positive. You see? So that means this one, this type is what? NPN. Okay, what about this type now? As you see, where is the arrow? Where does it point to? It points to the emitter. And usually its direction, this arrow, always its direction is towards the negative. That means the emitter will be what? Negative. That means the end will be what? Negative. That means now the base is here, as we said. That means this one is what? This one is negative. When this one is negative, that means also the other end is what? Negative. So that means the middle is what? Positive. So that means this one is called what? NPN. NPN. Okay, how do we get the gain of current? The gain of current here. How do we find it? The gain of current here. The gain of current in transistor. So the gain of current, it equals the current of collector over the current of what? Of the base. Just you find the current of the base, you divide by the current of the collector to do it. Okay, what about for, as we said, for the diode, we have something we call it drop voltage. Drop voltage, it equals, as we know, voltage, it equals I times R, but plus a small v here, we call it drop what? Drop voltage here. That means now when they start the electrons in the forward connection to move here, they have to overcome a specific here voltage in order then to start to move. So that means this one is called what? VF. Okay, microchips, by the way, or we call them integrated chips. They are small chips that they have thousands of transistors and diodes at the same time, and they are used in many electronics. Anyway, we understand now what is energy gap theory and how we understand through it when there is no gap between the conduction and the valence. That means these ones are conductors, and when the gap is around 1 to 2, in this case they are semiconductors. When the gap is 5 or more, these ones they are what? Insulators.